Okay, it is a recording, and no, or lecturer György Barabás, or usual moderator, but I moderate. No, and you are the lecturer, and story story.
Okay, can you see my screen?
Yeah, it's okay.
Excellent. So in that case, let us start. Thank you everybody for coming today. And the problem I'm going to be discussing is actually quite simple. Suppose that we have some sort of ecological model which produces a stationary but non-periodic time series, for example, because of environmental forcing. Here's a little example that you can see here. And now suppose that we change a parameter in the model. Say we reduce the mortality rate of species 1, the blue species. In that case, waiting a little bit, we will see that we get a new stationary state, which we have right here, where species 1 has a slightly higher average abundance because its mortality is now lower. And again, we can perturb the parameter further, and then its average abundance will increase even more, and so on and so forth. The problem we're going to be discussing is, can we predict these changes based on a baseline solution? Say if we know this solution, then knowing this and the model and what amount of parameter perturbation we apply, can we predict what happens in this and these examples? If not for the precise time series, then at least for the average abundance denoted by these horizontal lines. In order to be able to answer that, let us first try to answer a more modest kind of question, which is how does this work in periodic settings? So let's assume that the dynamics are exactly periodic. I'm plotting 3 periods here. And in that periodic setting, can we predict the average densities after a parameter perturbation? So again, the setting is that we have population abundances, and they're given by this kind of model where the population density of species I, Ni, at time t plus 1 is equal to the population density before times the geometric rate of growth in discrete time, Ri t. And this Ri of t is in turn a function of various things, and let me explain that. First of all, there is this script r mu of t. Those are standing for regulating factors. Regulating factors are all those parameters which mediate the feedback between population densities and population growth rates. In this case, the n's, which are the population densities, and the r's, the Roman capital R's, which are the geometric rates of growth. So regulating factors can be things like resources, predators, pathogens, refuge availability, and all those things that mediate the feedback between growth rates and densities. And the mu index says that we're talking about the muth regulating factor here, because we could have multiple ones of them. In turn, these growth rates are also functions of the parameter E, which, well, that is actually standing for the vector of parameters of the model. So for example, we could have a simple model where the per capita geometric growth rates are given by this simple exponential expression with sort of intrinsic rates, gi of t. Gi of t gives how much growth the species can achieve on 1 unit of the regulating factor. And that is multiplying the regulating factor itself, and there is a mortality rate, mi. And the regulating factor here, we can imagine to be in this model to be just some sort of spatial availability, say the number of nest sites that are available to use for the organisms, which is available to some maximum number of nest sites minus the sum total of the densities of the 2 populations. That is, we're calculating how many of these sites are being occupied at any given one time. So this is the availability of sites. So this kind of model, because of the exponential function, can be thought of as a multi-species, straightforward generalization of a Ricker map. We have this sort of Ricker style model. An important comment about the vector E of parameters. Their interpretation must be such that they are time independent. That is, in this model, you might be thinking, well, the parameters are this Rmax, the mortality is Mi, and the GIT. But that's not quite correct, because GIT are time dependent, and we define E to be time independent. What does that mean in practice? That if Gi of t is given by, say, an oscillating periodic function like this one, which in turn is given by the average plus an amplitude times an oscillating function depending on a frequency and an initial phase, then it is the mean, the amplitude, the frequency, and the initial phase that are part of the vector of parameters, not GIT of itself. So in other words, consists of these lower level parameters plus Rmax plus the MIs. So they are all time independent. All right, with that, how shall we solve this problem to be able to determine how a parameter perturbation changes the average population abundances in periodic dynamics? Now, we are theoretical ecologists. That means we love everything that's static and eternal and unchanging in the universe, and simply abhor anything that fluctuates, that changes, or does anything funky and anything even just ever so slightly more complicated than the absolutely most trivial. So here we are stuck with a task. How shall we convert this complicated problem of periodic dynamics into the trivial one of fixed points? And the way we're going to do that, there are many different ways of doing that, in fact. And in the past, with Geza, we have experimented with some of them. But the method that seems at least to have the most development potential in it is to pretend that population on a periodic orbit is actually structured based on time. That is, the population state at various moments along the cycle are the analogs of various age classes. And we have a Leslie matrix, which transitions the population vector from one period into the next period by multiplying this way. If you look at this matrix, it really looks like a Leslie matrix. It has only non-zero entries in the first subdiagonal and in the top row. So it's a Leslie matrix with a single reproductive H class at time t. The only place where the analogy breaks down slightly is that these numbers R I of t do not need to be between 0 and 1 because their growth rates are not probabilities. Therefore, these subdiagonal entries can be larger than 1, but that doesn't really create any complications. So we pretend that the populations in this community are actually at a fixed point, but they're structured based on time. And then the periodic orbit is actually an equilibrium point of the structured model. That is the key idea that we're going to be using. Now, if this is a structured model, then of course, this structured model for each species I has a dominant eigenvalue, lambda I. This dominant eigenvalue, because it depends on the matrix entries here, will also inherit their dependence on the regulating factors and the parameters. And since we are at the equilibrial state, the periodic orbit, the abundances along the periodic orbit themselves are functions of the parameters because they're equilibrium abundances, so to speak. That is, if we perturb the parameter, then the periodic orbit would also change and shift around. What is the value of this dominant eigenvalue? Of course, it has to be equal to 1, expressing the fact that throughout one period, nothing changes. We return to exactly the state where we were before. Now we perturb the parameter. We write that in by assuming that there's an infinitesimally small perturbation, dE, and add that to the parameter. So that will change these quote-unquote equilibrium abundances. It will change the parameters, so it will change everything, and it will change the lambda I to, well, it won't change, because the whole point of an equilibrium state is that when we perturb, we get back into some new equilibrium state at which the dominant eigenvalues are yet again are going to be equal to 1. And this is the key to dealing with this system. What we do now is subtract these two equations from another, do a Taylor expansion, and do the bookkeeping. Yes, the bookkeeping is somewhat tedious, therefore I am not going to go into their details. I'm just going to jump straight to the result, but in principle, the steps are straightforward. So let me tell you what the result is. The response of the average density of species I through the period to perturbing a parameter is minus the inverse of a matrix M times a vector Z. And the matrix M is given by this expression. The vector Z is given by this expression. In this expression, there is a matrix H inverse that I haven't defined yet. H is given by this expression here. That's what we have to invert. And there are two more symbols here. This delta AB, which is just a Kronecker symbol. It is equal to 1 if A is equal to B and to 0 otherwise. So it is simply an indexed notation for the identity matrix. And WKB is the Bth entry of the dominant eigenvector of species K. So these formulas look complicated, but let's not forget that they're all strictly expressed in terms of the unperturbed quantities. So if we want to extrapolate the behavior of the model to what happens when we change parameters, we don't need to know how the model behaves for those other parameters. We can just extrapolate using known quantities. Now, let's not belabor this formula. There will be time for that later. Let us instead see how this works in practice. Let us take the exact same simple model that I started with, and let's see how it works. Here I'm depicting the exact same periodic orbit that I showed you before. The only difference is that back then I was emphasizing the fact that it's periodic, so I showed you 3 periods in a row. Here I'm showing you just a single period because I want to concentrate on its details. That is one difference. And the other difference here is that you might notice a dashed line apart from the solid horizontal line, which, if you remember, shows the average densities for the species for the period. The dashed lines, on the other hand, show the predicted averages based on the perturbation formula. So as you can see, if the perturbation is small enough, the parameter, then the predicted and the observed values match up very closely. For larger perturbations, not so closely. That is natural, since we derive the formula based on the assumption that the perturbation is infinitesimal. As usual in sensitivity analysis for smaller perturbations, we can expect the formula to be more numerically accurate. Okay, how does the same method fare if we don't choose a period 7 oscillation like we have here, but something longer, say a period 100? Here's an example. This is strictly periodic. If you squint hard, then you can sort of see that the dynamics sort of loop into one another, and you could continue these curves going back to the beginning. So this is perfectly periodic dynamics with a 100 cycle. And as you can see, again, the formula, well, actually does an outrageously good job of predicting what happens. That is a happy circumstance, but don't expect it to be that good, of course, at all times. This is sort of an accident of the setup, and of course, we're happy when this happens, but this is not something one should just count on. To show you another example, here is a different kind of model than we have been looking at before, and I don't want to belabor it much. Most of you probably know it instantly. This is the so-called annual plant model, where we're modeling the abundance of seeds in the seed bank of organisms, and GIT is a germination rate of species I at time t, SI is a survival rate of species I in the seed bank, the Ys are yields, and alpha are sort of competitive effects. And then we have, again, an effective regulating factor here, which again is a weighted combination of the abundances of the species. I won't belabor the point here. The only thing is here, again, I generated a default scenario. It's right here, a baseline solution that is periodic with a period of 100 years. And here is the solution for species 1 and species 2, and then we change the survival rate of or rather survival probability from 1 year to the next of species 1 in the seed bank. I increase that likelihood, and as we increase it, we see that the average abundances change, and again, the predictions match the actually observed values very well, and even for larger perturbations, they're quite accurate, but even if they're somewhat off, they're qualitatively correct. Right. So far, this was all a sort of a practical set of methods that you can use to predict how models might behave if you change parameters, which is useful to have. Now I want to connect it to some more conceptual things, in particular to coexistence theory. Let us start from our perturbation formula that we derived, the response of the average abundances to a change in the parameters. It is equal to the inverse of a matrix times a vector. And this matrix is this hot mess of symbols. So it looks like something very indomitable, but let's actually try to tame it. If you squint at this formula from a distance with half closed eyes, then you can sort of see that it falls apart into 2 parts. This little chunk only depends on the species index I, and this chunk here only depends on the species index J. And I'm going to denote these by SI mu t and I j mu t with these symbols script S and script I. Let me tell you about those. Let's first talk about script S. Script S here, if we look at it, is the derivative of the log geometric growth rate, and the log geometric growth rate is just the usual per capita growth rate, as we usually think about that in ecology. It's the response of this growth rate to a change in the regulating factors. That is, how does the growth rate of an organism change if I suddenly give it a little more food? We can call that the sensitivity factor, because it measures the sensitivity of the growth of a species to a change in the regulating factors. You might have also noticed that we're summing over the index B, which is a time index here. I won't belabor that point, but the reason why that summation is there is because population regulation might happen with a time lag. It is possible that I do something here and now, but its effects will only manifest themselves a few days later. Of course, we don't expect it to be too much later. If I do something now, that hardly will ever have a direct effect on what will happen in 1,000 years. It might have an indirect effect, but not a direct effect that we're measuring here. So intuitively, this will decrease. So this sum will be finite. That is correct. But there might be some time lags in the system. That's why we have the summation. In turn, let's switch from the sensitivity vector to this one, the script I quantity, which I will call the impact vector. And this looks a little more scary, so let's break it apart to show that it's actually not. Let us just deal with that part of the definition there, which I will call the direct impact vector, and will denote with a little 0 in the superscript. The direct impact vector looks at the change in the regulating factors in response to a change in the abundances, and that is weighted by the total population abundance of the species, normalized by its abundance throughout the period. So that's just a normalization factor. Whoops, excuse me. So in other words, what we're measuring here is how would the food be depleted if we added in a couple of more individuals of the species J in this case. So it is the impact of species J on the regulating factors. That is why we call it impact. And we're multiplying with the population density, which just means that this per capita measure is converted into a population measure in the end. And the impact factor proper up here is just the same thing, the direct impact multiplied by the inverse of this operator H. Not to belabor the point, what's happening here is the following. When we perturb a parameter, it's not just the growth rates that change. It is the population structure that changes as well. If we insist on pretending that these populations are structured populations, structured through time. And therefore the population structure changes as well, but this simplistic direct impact vector does not take account of that. The matrix H inverse does. So when we multiply with H inverse, that is what takes into account the fact that the population, the stable stage distribution itself will have changed. Okay, so with these concepts in hand, let us look at what happens with this coexistence formula. In fact, just let me go back one step. If we look at, we substitute in S in place of this and I in place of this, then this whole formula just suddenly simplifies to this little bit here. What does it mean? It is the product of the ith sensitivity and jth impact and calculated summed over mu and t, which is time. So it is the overlap of these vectors with respect to mu and t, and notice that the role that these indices play, the regulation index mu and the time index t, is actually identical. I might as well merge them into one super index and sum over only that one super index, which would be an index which goes through all the combinations of mu and t. And then it would be like a proper scalar product of these two quantities. We can even express that in notation. Here you go. That's what I've just done. I've just pretended that these are vectors with respect to that sort of super index, and then we can just write their scalar product as usual, as is here. I have to emphasize this point because it will come back that the role that regulation indices and time indices play in this formulation are formally equivalent. Just remember that for the future. So we have the scalar product of the ith sensitivity and jth impact vectors. We might as well write it out in full matrix notation, substituting in 1, 2, 3, 4, etc. for I and j. We get this kind of structure. Now, the thing we should notice here is what happens if, say, two of the sensitivity vectors are identical, say S1 and S2 are equal to one another. If S1 and S2 are equal to one another, then quite obviously and manifestly, these first two rows of the matrix will become identical to one another. Even more is true, even if the S1 and S2 are not exactly equal to one another, but say just proportional to one another, then the first two rows of this matrix will also be proportional to one another. The same exact thing is true for the impact vectors. if impact vector for species 1 and the impact vector for species 2 are equal, then manifestly the first two columns of this matrix will be identical to one another. And if they're proportional to one another, they will be proportional. And more broadly even, we could say that if a certain set of rows, a certain set of sensitivity vectors form a linearly dependent set, then the corresponding rows of the matrix will be linearly dependent, and mutandis for the impact vectors and the columns of this matrix. Small remark, I had been talking about the impact vectors here, but the exact same thing is true of the direct impacts, which are much simpler to think about, because remember, this matrix H inverse is constant. It does not depend on species indices. That's an important property it has. So it's the same matrix everywhere along here. So you can see that, if, for example, the direct impact vector of species 1 is equal to the direct impact vector of species 2, then the first two columns of these matrices are equal to one another, and so on. The same about linear dependence, and so forth. Okay, so we've established these kind of rules for linear dependence. What follows if either the sensitivity vectors or the direct impacts are linearly dependent or nearly linearly dependent? In that case, the matrix M will be ill-conditioned, right? This is the matrix M that we've been working with. It's ill-conditioned because it has two rows or columns that are nearly identical, therefore its determinant is close to 0. And that also means that the entries of the inverse matrix would be large compared to the entries of the original matrix. But if that is large, then that means that this derivative of the response, so the response of the average abundances to a change in the parameters will also be large, since that, by our perturbation formula, is proportional to this matrix inverse. But if that is true, that means that coexistence is fragile, because if the average abundances exhibit a large jump, even for a small perturbation of the parameter, that means that we can very easily get out of the feasible range of abundances, get a negative average abundance, for example, and then coexistence is lost. Let me illustrate that idea. Here, I'm plotting the components of imaginary sensitivity vectors for an imaginary community of two species that are regulated by three factors, say nitrogen and two herbivores. So these are plant species here. So they take up nitrogen from the soil, and there are two herbivore species eating them. As you can see, they exhibit very similar proportional responses to each of these factors, which would mean that their coexistence cannot be robust. Essentially, whichever species is better at obtaining nitrogen and avoiding the herbivores will win between these two. However, what happens if we have periodic dynamics with a 2 cycle, and between the two time period points, the sensitivity vectors are different between the species? This can save coexistence, because now the full sensitivity vectors of the species are not actually proportional to one another, because at time point 1 they were, but at time point 2 they aren't, and therefore these curves as overall functions, again, remember it's both of these indices, the regulation and time indices, that matter. Overall, all the combinations of all those indices, these species differ enough that at least robust coexistence is possible. Of course, if what we would find is that in the second time point, we would have this kind of setting, then again, it would still be very hard to achieve coexistence, because these vectors are very much proportional to one another. That would mean that this matrix M is ill-conditioned, and therefore even a very, very tiny change in the parameter would cause an unreasonably large change in the average abundances. Therefore, species would not survive a perturbation of the parameters. Okay. So far, we've talked about periodic dynamics. How do we extend all of this to infinite times? The goal of extending to infinite periods is to be able to talk about actually stationary aperiodic dynamics. And that is a bit of a trick. Let me talk about that briefly. In order to do that, we have to assume stationarity still. That is the overall dominant eigenvalues of these infinite operators that they become in the t goes to infinity limit. Those are still 1. we have to be careful to ignore certain funky edge cases, which will give us trouble. This kind of dynamics, where the population density of a species changes in this periodic manner through time, that it exponentially declines and then it suddenly jumps up, then exponentially declines again, and then it jumps up suddenly, and so on and so forth. These kinds of dynamics do not have a proper extension to infinite period time, because as I extend the period from 50 to infinity, we'll just get exponential decline all the way through, so we cannot maintain stationarity. So we have to ignore these kinds of cases and really stick to ones where we can ensure stationarity. And then we have to take the perturbation formula we derived and try to take it in the t goes to infinity limit. How can we do that? Well, let's write out the matrix M, which is equal to the sensitivity vector times the inverse of the H times the direct impact vector. Now, as for the sensitivity and direct impact vectors, I won't belabor that point. The point is that they, as time goes to infinity, they have infinitely many components, t and tau in time, but all of them will be finite. Not just finite, they will be bounded. That is, they won't behave badly as time goes on to infinity. So that is fine. And if this matrix here was just the identity matrix, then we would have the scalar product of these two vectors, which consist of the sum of infinitely many products that are themselves finite and bounded. That diverges, however, we have the factor 1 over t here, which normalizes it, so it's all well behaved. The problem is this matrix H inverse. What can we say about that? It's not just that H inverse has to have bounded finite entries, it's that H inverse should have bounded row sums or column sums. Because if it doesn't, then when we apply this matrix to either the direct impact or sensitivity vectors, then we would get vectors whose entries are not actually bounded. Are the rows or columns, row sums or column sums of the H inverse bounded? Well, not necessarily, but one thing that we did manage to prove is that if this particular derivative, which, if you remember, is part of the impact vector, is independent of the index tau, then the column sums of H inverse are finite and all is well. Is this a realistic condition? I don't know. Naturalists will be able to tell that better than I can. However, one thing I can say is that in that simple toy model, which I introduced to you to show the ideas of, this condition is actually true. So there are at least models that are reasonable, and this condition is fulfilled on them. I emphasize that there are probably more conditions when this is true. It's just that in this case, we can actually prove it explicitly. This vector z is actually more problematic because of this crazy sum that you have here, which actually is not convergent, because as the index b goes to infinity, as t goes to infinity, this diverges, and that does create problems. The saving grace is that if you look at the matrix that's multiplying it, this is the normalized dominant eigenvector for species k, so its entries sum to 1, and this is the identity matrix whose row sum is also 1. So the row sums of this matrix are all zeros, and that seems to actually take care of this, at least in certain special cases. One can show that that is the case. So as by magic, the divergences cancel out, and we actually end up with a finite formula. Again, for special cases like these ones, one can show these, but otherwise finding general proofs is very much work in progress. And if you're interested in thinking about these things, then we're actually would be very, very happy to have people help us with these kinds of things. Me and Geza have been thinking about this problem for some time now, and we would be very happy to have some ideas. All right. One last thing I wanted to say. We talked about the structure of, actually not the last thing, sorry, 2 more topics I wanted to talk about. Here's the next one, sorry, don't want to create false expectancies. So we extended the theory to infinite periods, and we've recognized that every regulating factor at every given moment of time behaves like an independent regulating factor. The results that we've seen earlier can be summarized by saying that the community ecology, coexistence in a periodically fluctuating environment is just like coexistence in a constant environment with constant abundances, except that the regulating factors have to be counted differently. Every regulating factor at every different moment of time can count as a different regulating factor, and that is because of that summation over both the regulation indices and the time indices that we had. Now, in the case that we extend the period to infinity, doesn't that allow one to have infinitely many regulating factors and therefore just explain away the coexistence of as many species as we want to? Well, not really. And I want to give a feel for the reason why. Look at this hypothetical sensitivity vector. This is the sensitivity vector of a given species, just one species, which has small entries here, then large entries there. So it's very sensitive to these small-ish somethings or another that I haven't specified. Then it drops down, and for medium and large ones, it's again small. Okay, what the heck does this axis actually measure? Well, if this is resource size, so we have, say, small seeds to large seeds, and this is a bird species which tends to eat smallish seeds, then all is well. This is a perfectly fine sensitivity vector. However, if this is actually a single resource that species eat and it is structured by time, so this is the timing of the resource use, then this species is in trouble because species cannot afford to simply be sensitive to a resource at one given well-localized time and then ignore it for the rest, because species have obligations through time. Putting it bluntly, you simply die if you don't eat at any other point of time than in just one very short window of opportunity. And that means that if we have timing of resource use, the sensitivity vector will not look so much like this, but more like this, that you constantly have to rely on the resource. You will have constantly some sort of sensitivity to it. And this will make the vectors, even though they mathematically behave identically, biologically, there will be some difference, because if you have resource size, then it's perfectly conceivable to have, say, 5 species, each of which have localized resource consumptions. This species eats large resources, this one somewhat smaller, and so on to small resources. And if you notice, even adjacent species here overlap in a very limited way. Therefore, their sensitivity vectors are not very proportional to one another, so robust coexistence is possible. But if we have timing of resource use, then the other species, well, they will have to do something like this. And this is much messier. It's much more difficult to avoid overlap between different species when we have this kind of scenario. And therefore, while it is possible to get multiple species robustly coexisting through this mechanism, you cannot just pile it on and say, oh, now I have an infinite period length, I can pack in infinitely many species. Not quite, because you have these obligations through time, and therefore some overlap will be simply forced in these cases. I guess there's another way of saying the same thing, which is that if we really have a stationary process, then if that stationary process has a characteristic time scale, then by considering times that are larger than that time scale, we don't really gain much more information. All the essential information is there in the quasi period, so the characteristic time scale of what's happening, and that's really where species can play and carve out an existence for each other, not for the whole infinite time axis. So all I'm saying is that yes, we can extend this theory to infinite times, and yes, the exact same formalism still works, but that doesn't mean that species can just coexist the way they want to, because biologically speaking, they're forced to have sensitivity and impact vectors which are more or less spread out across the whole time series, where that does not have to be true for, say, resource continua. Okay, one sec. Thanks. Now, a wise man would stop the talk here and let questions happen. So by modus tollens, I will go on. And not just because of the modus tollens, but also because I'm pretty sure that there are some people in the audience who would ask this question if I didn't bring it up, and therefore I will talk about it a little bit anyway. And that is, okay, very nice. I described a way of thinking about coexistence in variable environments. But it's not like ecologists haven't thought about this problem before. We actually have well-developed theories of coexistence in variable environments. How does all that, which I have been talking about, relate to those established theories? In particular, how does it relate to Chesson's coexistence theory? Well, in Chesson's theory, just to recap quickly, we approximate the log growth rates with a quadratic expansion, which with a clever choice of parameters looks like this, with an especially simple form, which consists of a density and frequency independent part, a part which is called the competitive parameter, which is density and frequency dependent, and the interaction term between the two. And yes, the interaction term is just this simple. That's the only quadratic term, because these parameters are defined in a clever way to make that true. And this parameter gamma measures the degree of interaction between them. Then we take averages of these in time. And after, so we end up with the average of this term, the average of this term, and the average of these terms, where because of the nature of the approximation, because we assume small fluctuations in Cheson's theory, we neglect the product of the means, because those will be quadratically small, and we only left with the covariance term. And then we perform an invader-resident comparison, where we calculate the difference, a sort of a weighted difference in the log growth rates between invaders and residents. And that will give rise to terms which are proportional to the differences in these density and frequency independent terms. Those do not contribute to coexistence. Those contribute to competitive exclusion. But these terms will contribute to coexistence. This term is called the relative nonlinearity, and this term is called the storage effect. Those of you who know this will know this very well. Those of you who don't, I'll just mention very quickly. The reason this is called relative nonlinearity is because actually the way these terms are defined is that if these competitive factors are linear in underlying regulating factors, those will be canceled out. Those don't make a difference. So there has to be some sort of nonlinear response to those factors in these functions in order to make these delta terms non-zero. And those can contribute to the growth rates of the invaders when rare. Therefore, there are two mechanisms, really, two distinct mechanisms which arise from this quadratic expansion of growth rates. That's one term, and that's the other term. There's relative nonlinearity and the storage effect. By contrast, in the sensitivity approach that I was showing today, there is no invasion analysis. We have a stationary state that we're analyzing. Whoops. There is no direct time averaging either. I put direct in parentheses because we are calculating the response of the average abundances, but we're not doing the time averages of the growth rates like they're done in Cheson's theory, and we're not making small fluctuations assumptions either in this case. What determines coexistence is the overlap in sensitivity vectors and overlap in impact vectors. And really, there's just a single mechanism that is temporal niche segregation, if you will. Segregation in the sensitivity and the impact vectors. That's our mechanism. So we don't have these two separate things that we have in Cheson's theory. So just to show you more of the connection, how would we treat, for example, relative nonlinearity in our framework? So for example, we have a model where we have two species with growth rates which look very much like we had in our simple model, except notice that the regulating factor is squared in the growth rate of species 2. And also I made these G parameters here time independent. That I did to make absolutely sure that there is no storage effect in this model, that any coexistence is purely a consequence of relative nonlinearity, and in fact that's what we have. These dynamics generate a stable H cycle indigenously generated by the dynamics itself, so this is not externally forced, and we end up on this stable H cycle. How do we treat relative nonlinearity in our framework? The simple answer is we don't. We just follow our standard procedure. We calculate the sensitivity vectors. Here's the result. We don't need to go into the details of the calculation. And we calculate the direct impact vectors. And once we have those, we can plot them against one another. We have the sensitivity vectors of the two species here and the impact vectors here. As you can see with the sensitivity vectors, well, one of them is constant, the other oscillating. So clearly there's some limited overlap in between them, not complete overlap. The impact vectors overlap much more. So this would make robust coexistence more difficult, but not impossible. And in fact, what we see is that we can get stable coexistence. It is quite sensitive to parameter perturbations. I've tried it. So this is not hyper robust in terms of coexistence, but there's a possibility for it as shown by the sensitivity and impact vectors. All right, this is all good, but maybe not so convincing. So the thing is, no matter what we otherwise think about these things like relative nonlinearity and the storage effect, we've learned to live with them because they're so damn useful. And therefore, even if they are difficult to interpret, we've found ways to interpret them and to get around them and to think about them in somewhat intuitive ways. Therefore, it is important to make an intellectual connection to how we conceptualize these concepts like relative nonlinearity and storage effect in the sensitivity framework. Let me show you an example of what we can do with the storage effect in particular. So we start out from our matrix, which we invert in the sensitivity formula, which is simply the overlap between sensitivity and impact. For simplicity, let's just assume that we have a single regulating factor because we want to concentrate on the effects of time here. We have the overlap between these two vectors, which we can also write, well, it's actually their time average because we multiply by 1 over t. So I denote the time average with the overbars. We have the time average of s times I. And the time average can be written as just the product of the averages plus the covariance between these two quantities. What can we see from here? The first thing we can see is that there can be absolutely no robust coexistence without the covariance terms, because if these covariance terms are 0, then we end up with this matrix, and notice that they all have linearly dependent rows and columns. This is in fact a rank 1 matrix by itself. Therefore, we must have covariance terms if we want to have coexistence. The second thing that we observe is that imagine a scenario where Sij, the covariance between Si and Ij is sort of small if I is not equal to j, but strong if they are equal. So the diagonal covariance terms are strong. That will add a constant to the diagonal of this matrix as a whole, and therefore beyond the point improve the robustness of coexistence, because adding a constant to the diagonal of the matrix shifts the eigenvalue spectrum as a whole in one given direction, to the right if they're positive, to the left if they're negative, and therefore after a while it will bring them away from the imaginary axis or the eigenvalue. So beyond the point, diagonal covariance terms improve robustness. However, you might be thinking that, well, if we add these terms, then we're destabilizing the system because we're bringing the eigenvalue distribution towards the right. That is correct. Only negative covariance term confer stability because they bring the eigenvalue distribution towards the left, and therefore they stabilize the system. Now, if you think about these conditions, you need species-specific responses to the environment through these covariance terms. You need diagonal covariances between sensitivities and impacts, but you need some sort of buffering with growth. That is, you need a negative covariance between sensitivity and impact. That means you shouldn't, when you're in a sensitive phase, you shouldn't overdraw your resources. That's what this means. Those are really reminiscent of the conditions for the storage effect that we talk about. So in this way, the framework that we have encodes in itself also the storage effect. The one final question that we have left is, okay, that's true, but is the covariance of Si and Ij really proportional to the covariance of the environmental and competitive factors of Chesson? Because we haven't shown that, and I won't belabor this point. I'm happy to share the detail later with those who are interested. All I will say is that they're sort of related to one another, but they're not exactly the same for sure. However, you shouldn't worry about that because, as we've shown, this kind of description that we have here is more complete than the Chesson description. This one involves both the storage effect and relative nonlinearity together in one unit, which means we no longer have to worry about this somewhat artificial partitioning of mechanisms. Instead, we just have one mechanism which encompasses all fluctuating mechanisms in one unified manner. And with that, I thank you very much for your attention, and I am happy to take any questions.
Thank you, György. Thank you. And any question, comment from the audience? Andre, please unmute your mic, okay, and please start again.
I think I gave the wrong reaction. I wanted to clap, so that was my reaction. Okay. I don't have a question, Geza.
Okay, then another.
Okay, thanks for the talk. So it was extremely interesting, and what I would like is to get some intuition. I know that if you have a neutral model, then it is extremely sensitive to any perturbation, right? Neutral dynamics. So if I just take one species and color half of the individual thread and half of them blue, then they will generate automatically these two dependent vectors that will make your matrix ill conditioned, right? However, why
this one?
Yes, why by and large, if I have apparently, if I understand you correctly, you suggest that in any case where two species have very similar response to some external given or a set of external parameters, then it induces some sort of sensitivity or ill condition of the matrix, or the situation is very sensitive to small perturbations. And why is that? This I don't understand.
Yeah, so it's actually not the sensitivity with respect to the parameters, but sensitivity towards the regulating factors and impact on the regulating factors.
Okay, yes.
I did not get better. I know this is crappy because I should have somehow visualized these quantities here, but I have no idea how to do that. So the idea is that say we have a regulating factor, and to continue with the neutral example, let that be space. So there are two species of plants competing for available slots on the landscape.
Mm-hmm.
And then proportionality of the sensitivity and impact vectors, in that case, since we have two species, but only a single regulating factor, unless we have some temporal perturbations, it's basically forced, right? And then we know that there's no robust coexistence. The idea is, so what you want to get an intuition of is, what does it mean for these to be proportional?
Yes.
So what that would mean is that the species respond in the same way to population regulation. That if we open up some more space for them, they will respond by and large in the same way, and they impact those spaces.
Yeah, this I understand. What I don't understand is, yes, why this causes instability.
So intuitively, the reason is that if we have this kind of situation, then any small advantage one species can have over the other will be decisive. So for example, we have these species which respond identically to space, but one of them has a lower mortality rate. So then they're pretty much equivalent species, it's just one of them dies less. So it's going to exclude the other species. I'm not sure I'm quite getting at what you're trying to ask, though.
Okay. Thanks.
Okay. Anybody else? Steve?
Hi. Yeah, thank you for the talk. This is very new and interesting. And I'm in sort of in the Dav's shoes. I'd like a little more intuition, if somehow. And the way I often do it is by asking myself, what does this say about the lottery model? So what does your theory say about, let's say, a non-neutral lottery model, about how you get coexistence in the the original lottery model, where one species, where they're the same, but one species has a higher mortality rate?
In fact, I don't know. I know this is not the lottery model, but it's in the same in spirit here, right? The annual plant. Is that good?
I think it's the same in spirit if the denominator all the way on the right is the same for everybody.
Exactly. Yes. So what we'd do then is first we would calculate the sensitivity vectors, which would be quantities which depend on the timings, right? Because they would depend on GIT and YIT. If there wasn't a time dependence, then we would immediately see that there can be no coexistence, because then the two sensitivities would just be proportional to one another. Whereas if their timing is different, then I can plot out in time how the sensitivity vectors, which again is just the derivative of this with respect to the regulating factor, how the derivative changes in time. So that's where we might get say a figure like this, and for now forget about nitrogen or herbivore. Imagine just that these are different time points, 1, 2, 3, 4, 5, 6. So then we might get that at different time points these species behave differently, and that will enable them to coexist. If they responded in the same way at every moment of time. So if they did something like this, this would make it very difficult to make robust coexistence. And for the impact side of things, it's similar. It's just that for the impact, we take this quantity here and take its derivative with respect to the abundances and weigh it with some other abundances. We do that kind of weighing. So it's essentially the derivative of the regulating factor with respect to the abundances, which again is a vector in time, and which we can plot out in the same way and see if they are similar to one another. So I guess the intuition is if we have two species in the annual plant or lottery model, and they impact the environment in the same way at every moment of time, and they're sensitive to it in the same way at every moment of time. And by same, I don't mean exactly the same, I mean proportional to like this. Well, in that case, possibly species 2 will win in this case, because these are sensitivities, and species 2 is less sensitive in a way to the vagaries than species 1 here. So presumably what's happening is that species 2 is just like species 1, just a bit more efficient at everything. But if they can partition the responses, because say there's some seasonality in our annual plant or lottery model, and one of the species does better in one season and the other does better in the other season, then there's a possibility for robust coexistence, because then the sensitivity vectors will differ between the species and the impact vectors as well, depending on season, and therefore for the whole period or just stationary time series, they will not overlap with one another.
Okay.
And once
Thanks.
again, I'm not sure if I properly answered the question, so please feel free to ask follow-up questions.
Well, we've got some other hands up, so I'll let other people jump in.
Okay, then Jeff, please the next.
Oh, yep. Hi. I don't know if you hear me.
Yes.
Good. So, okay, I have a few questions. One of them is I'm a bit surprised by the convergence issue, because you take this limit of stationary signals that are not periodic as the limit of longer and longer period. And I mean, I don't know, I don't have any counterexample, but I was wondering if there was a mathematical results that prove that this is how you can think of stationary aperiodic signals.
I don't think there's any particular result, and I do not want to claim that this is the way to think about it, or even that this is somehow the best way to think about it. However, it does seem to work. So we've tried other things in the past, such as designate an initial moment in time, and then create the stroboscopic map, and then try to look at what happens if the stroboscopic map is such that, or the Poincaré map is such that the period goes to infinity, and those approaches really didn't work. And this one at least seems to be consistent, and at least for particular model examples, it checks out. So at least there's some evidence that at least it's not completely out of whack, that it's not completely crazy and not by default self-inconsistent. How far one can push this, I don't know. Maybe you want to help us with it.
I don't know. Also, because here you look at the sensitivity of the mean, and so if it's very sensitive, then you conclude that coexistence is going to be difficult. And it sounds, yes, it seems like that the mean is not too sensitive would be a necessary condition, but it's not sufficient necessarily, because maybe the mean is not sensitive, but
the variances.
The variance might be.
Absolutely. I would think of these anyway as a necessary condition, because in any case, even if we have a situation like this, these sensitivity vectors do not fully overlap. Therefore, the way I would phrase it, and the way I tried to phrase it during the talk, is that there is a possibility for coexistence. It's not out of the question that this would lead out of coexistence. But this one is sure as hell will, because there's just no way to keep this matrix in check. I guess that's the way I would phrase it. So you're absolutely right. This is a the smallness of this derivative is necessary for coexistence. It's not sufficient.
Okay, and so just a small last question. Since you divide into an infinite amount of time steps, and you need you basically take sensitivity, like your sensitivity and impact vectors, they basically lie on this infinitely large discrete space. It seems like you would need an infinitely large amount of information to make predictions. But is there, yeah, I mean, I was wondering, since it's also kind of an averaging, maybe there are averaging effects underlying that make some generic quantities pop out that are not, that you know, like something a bit more robust than having to, the need of knowing, I guess is what you hint at when you talk about temporal niche segregations and these such behaviors.
And also what I was trying to say that if we have a stationary fluctuations with a characteristic time scale, then we don't really add much information by including even more time steps than the characteristic time scale of the fluctuations. Right, so that yeah, of course we always add a little, but that little becomes more and more insignificant. We won't radically change the outcome precisely because this is not realistic. This we cannot do with time. That species one reacts to time here, and then for the rest of eternity it just doesn't do anything. I mean, such a species cannot survive. So you know, you must be always active to maintain yourself. You have obligations through time, as evolutionary biologists like to say.
Can we switch to the next question?
Yeah.
So, Eva?
Yeah, hi. I'm wrestling with your comparison of this approach with Chesson's theory, because if I get you correctly, you can't even evaluate this matrix M without having actually a time series of population densities when the two species coexist. So we know beforehand kind of that they coexist at least for some fixed parameters. And the Chesson is based on an invasion analysis. So there we don't have to have an example where we see the two species coexisting in the first place.
Yeah, that's probably about right. I would say though that in what we do, we don't necessarily need, yes, of course, formally the method starts out from a baseline unperturbed time series, but we don't really need to know the details of the time series because in order to evaluate the overlaps in the sensitivity and impact vectors, it's often sufficient to just know statistical properties that they have, because their overlap translates into some sort of covariance terms and products of means. But that's just to say that we don't necessarily need to know all the details of the time series to say something meaningful about coexistence. But yes, I guess you're right. Yes, so
you do evaluate those derivatives at the densities in the time series.
Yes.
So then you need to have them.
I mean, so if I want to quantitatively evaluate them, then we definitely need them. But if we have some sort of empirical way of measuring these things, for example, we have this feel that the annual plant model is a good model of the system that we're having, and then we can derive the sensitivity and impact vectors. And then if we have some information on the statistics of the fluctuations of the environment and of the abundances, then we can just use those. But maybe you're trying to aim at something slightly different.
Well, I guess I can't go further at this point.
But in any case, I will say that I think you're right in the sense that with Chesson's theory, Chesson's theory is also about stability. That right. Will these two species coexist? And our question is definitely different, subtly but different, which is, will the coexistence of these species, which we take for granted, be overly sensitive to parameters or perturbations?
Right.
Okay, then Rafael, please.
Thanks. So, György, so if I understand the argument for the collinearity of the sensitivities, I think what you're saying is if they are proportional to each other, then if one species does better than another under one circumstance, it would do better than that other species in all circumstances, and that's why it wins. Is that right?
I think so.
In the case where the sensitivities are proportional.
Like this one.
Yeah, because you're treating time as a resource, right? So
Yes.
like them being proportional just means that, you know, they never cross. So if one species is better at one point, it's always better. Okay, I guess that will be the intuition, if I'm not.
Oh, thanks. Yeah.
Yeah.
Yes.
Okay, so
that is
but
not
my
bad.
question is, right at the beginning, you treat the model as a stage structured model, right? And unless I'm misunderstanding, doesn't that assume that you're the abundance, the state of the system in the next time window, at each time point in the next window, is a function of the state of the system in all time points in the previous time window?
Yes.
So that will make this model not a Markov process, right? So you need to know not only what the species were like in the previous time point, you need to know what they were like in all previous time points.
So this might lead back to what Eva was asking about, well, you need to know the whole time series for the to be able to evaluate the formula. And that, I mean, that's basically correct. Yes, you do need to know this information. Again, unless you, for example, have some other kind of access to it, like measured data on empirical systems, where you can try to use that.
But that is very different from the types of models that we usually do, right? That they're typically Markov.
So this is what you mean, that this is the prime here just means that it's a whole period later than this.
Right.
And
right. So for instance, ni2 prime is a function of all of the ni t, right? Not just you know, one time in the past or exactly one period behind. It's all of the time points in the previous period. Well, I mean, most of those elements in the matrix are zero, so I
exactly.
guess
I think it's actually only a function of the previous step.
Right, because of the structure of the matrix. So now looking at the matrix again. Yeah. Okay, that makes sense. Okay, so I just have one other question, which was the analog of time as a resource. And you said if you want to make it stationary but aperiodic, you just draw the period to infinity. That means infinitely many resources, which doesn't mean infinitely many species coexisting, because there are conditions for the sensitivity profile when time is the resource compared to when something else is a resource, like seed size. So where in the model does that appear? Because it did appear that to the model there is no difference.
Very
right,
good question,
time.
and that's it. I think that's the answer. Nowhere. It's nowhere there. Formally, there's no difference. It's really just in our head or our knowledge of the world of biology that this in a way must be the case, because meaning you could write a model where species behave like this in time, and if it's a continuous density model with no demographic stochasticity, this might even work, because technically an exponentially declining population never actually goes extinct. But it's just that these kinds of models will not really have much biological relevance. We feel that these models have more biological relevance, where the sensitivities in time and impacts in time look more like this. But if we accept this, then it's more difficult to pack in lots of species, more difficult than, say, in this case.
Okay.
What's going on? Yes.
Yeah. Okay, that makes sense. So, and the biologist of this will be like you said, the analog for the case of seed size. If the sensitivity is concentrated on the left side of this axis, that means the bird focuses on small seeds. For time, exactly. That would mean the bird eats early in time.
Exactly, and then never
again.
Then you die, I assume.
So that's just a time series that you would never observe.
Exactly.
With more than one species.
Exactly. Okay. Yes.
Okay. Thanks.
Yep. Thanks.
Okay, Bob, did you want to say something? You has a hand up, and then.
I think my question was more or less asked by some of the previous people. Very nice talk, very interesting, György. I was thinking of an analogy here, and I don't know if this is useful, but my colleagues Richard Makaiwas and Joel Kingsolver in evolutionary genetics, you know, you have the G matrix, which is, you have a finite state space of, say, body size as a function of stage, but of course time is a continuum, and so they've done a lot of things with infinite dimensional, functional functions rather than, matrices describing things. And for any period like this, time is a continuum. And so you have an infinite number of matrices that actually are describing it, right? And but there must be some continuity principles that relate those matrices, because 2 points in time, things in between have to be connected in some way. They can, you know, maybe with some kind of weird white noise environment, that's not true. But most of the time there'll be temporal autocorrelation in regulating factors, for instance. Exactly. And I just think that might be something worth thinking about, sort of how you know, different ways of breaking up, you know, a given period into pieces, and thinking about what shows up when you look at the continuous version of this.
So notice that we've very carefully drawn time series here, which do have this kind of smoothness that you're talking about. That right. What happens in between 2 time points is sort of the trivial thing, which would not be true for the white noise. So what you're asking, we actually have done, although it was on an earlier iteration of this method, which had mistakes, mathematical mistakes on it, so we'll probably have to redo it. But it seems that the continuum extension is reasonably straightforward. Yes, one has to replace this H inverse with an integral operator instead of
right.
of this matrix. But that's maybe conceptually means something, but really doesn't introduce any new ideas. So as far as we understand, knock on wood, this extension is possible and will give the sort of expected result.
Great, thank you.
And Axel?
Thank you. I just wanted to suggest, if you would take the Fourier transform of this graph which you showed now, then you would have something which is more compact along the now frequency axis, and then maybe you see the niche separation better.
That's actually very
do
good
this
idea.
also for the many.
So what you're saying is that if the time series is actually stationary, then the Fourier series cannot have too big or too small components.
Right? Yes. So the smoothness means the Fourier transform declines quickly. That's
exactly. So that it's
then,
reasonably well defined where the frequencies are. And then one could maybe describe coexistence as a specialization on these Fourier modes.
Exactly.
Absolutely. I don't know off the top of my head how to do it necessarily, but yes. Yes. I guess the one thing I'm thinking about is what we do with, of course, our models are nonlinear, but since the whole method with the infinitesimal parameter perturbation is based on a linearization, so maybe it is totally possible.
Yeah, you can simply transform these scalar products between the S's and the I's.
Oh, yeah, you're right.
Summation, you transform it into summation in Fourier space.
Yes, and of course, the Fourier transform preserves the scalar product. So everything will be the same. It's just we're expressing it in different coordinates. Oh, that's a very good idea. Thanks.
Yes. And Robin, you wrote something to the chat. Could you tell us instead?
You wouldn't just, yes, you could specialize on mode if they were operating at different frequencies, but you could also specialize on phase if they had the same frequency but were separated in time.
Mm-hmm. Oh, good. Yes. So in other words, okay. So you specialize on your complex frequency, or which has both phase and.
The phase segregation you already had in your circular model. Oh.
But yes, I mean, that is a good point.
Yeah.
Yes.
Anybody else? If there is no more, then thank you for your lecture. And our next lecture, 2 weeks from now, will be by Priyanka Marasekare from the UCLA, with the title Predicting the Effects of Climate Warming from Chemistry to Evolution.